Welcome back. This is more dynamics practice, number 7 and probably 8 from the practice package. A sled with a weight of 702 newtons is placed on packed snow. Okay, so horizontal surface, and on there we have a sled. Its weight is 702, so gravitational force, someone worked it out. I don't like using W for weight because we use W for work. And admittedly, we also use delta E for work, but I'm trying not to use letters that overlap too much, so that's why I use the slightly weighty term gravitational force to talk about weight. And when something like a sled is sitting on a hard surface, like packed snow, there'll be a normal force pushing up, and we normally expect that to cancel out the weight. So those two forces are equal and opposite. That's why the sled neither sinks into the ground nor floats up into the air. The net force in the vertical direction is zero. Now, they want to slide the sled across level snow at constant speed, and the coefficient of friction is 0.012, so they aren't giving us the friction, but they're giving us enough to find it. The coefficient of friction is 0.012, that's pretty slick, and as you may know, that's FF. Frictional force is calculated by mu times the normal force. Coefficient of friction is 0.012. The normal force is 702 newtons. And out comes the calculator. 0.012 times 702 gives 8.424. 8.424 newtons for the friction force, and assuming we're pulling the sled forwards, the friction force will drag back. It's always opposite the way the object's trying to move. So if we want constant speed, meaning zero acceleration, we need to pull forward just enough to cancel out the friction. Our forward pull must also be 8.424 newtons. Anytime you want something to just cruise without speeding up or slowing down, you want all the forces on it to cancel. So however strong friction is, we have to pull forward exactly the same amount. As long as you do that, the net force on this is zero, and then, like Newton's first law says, it will remain in motion because it's not being acted upon by an external unbalancing force. If you wanted to do that mathematically, I'll show you this quick, but we don't normally bother doing this, but you could say, if you wanted to formulate this with Newton's second law, F net equals ma. The net force, looking just horizontally, would be our applied force. That's the force that we're doing, plus the friction force equals ma. And if you put numbers into that, you would get the applied force plus friction is negative 8.424. Because it's oriented to the left, I'm calling it negative, equals the mass of the sled, which I could calculate in a moment, and constant speed means the acceleration is zero. So if you put that in and then solve for Fa, you find after a few steps that the applied force must also be 8.424. So generally we don't need to do this because it's easy enough to see that these forces have to be equal and opposite, but if there get to be more forces, or if you just want to reassure yourself you're doing it right, you can set up Newton's second law and solve this. It works perfectly fine. And now we go to speedboats. A speedboat could start from rest. Start from rest, you remember in kinematics, means v initial equals 0. And accelerate to 50 meters per second, so we have a velocity later of 50 in a time of 8 seconds over a distance of 200 meters. Uh-oh. This is trouble. They're being too generous with the information. Determine the magnitude of the force propelling the boat forward if it has a mass of blah. Okay, well, the way we generally get force is we do mass times acceleration, and they've given us the mass, so we need an acceleration. So, thinking back to kinematics, is there any way that we could use this stuff and get an acceleration? Definitely yes. In fact, I think there are two ways. Option one, acceleration is Vf minus Vi over t, or your sheet might say delta V over delta t. If you do that, you get 50 final velocity minus 0, the initial velocity, over 8 seconds, which is 6.25 meters per second squared. Or, just for grins, let's do this a different way. We could also use Vf squared equals Vi squared plus 2AD. If we do that, we get 50 squared equals 0 squared plus 2 times an acceleration I'm pretending I don't know times 200. 50 squared is 2,500 equals 2, well, 2 times 200 is 400. Let's mush those together. And if you do 2,500 divided by 400, you get, lo and behold, 6.25 meters per second squared. So, as we saw in kinematics, there's often more than one way to get to an answer. And since we got 6.25 both times, we're feeling pretty good about that number. Now that we have it, we can find force easily enough. The force it takes to move something equals how massive is it times how fast do you want to accelerate it. And in this case, our mass is 50. Oh, okay, this is not your grandpa's boat. This thing's 55 tons. And its acceleration is 6.25 meters per second squared. 55000 times 6.25. I get 343,750 newtons. Now, precision-wise, these two numbers only have two significant digits, so we have to trim this way down. We could say, even if we went to kilonewtons, we'd still be saying 344, which is too high, so we have to go to scientific notation and just say 3.4, the first two digits, times 10 to the 1, 2, 3, 4, 5 newtons.